Hey everybody, welcome to lesson 31. This is light as a particle. So as you remember, the last couple lessons we talked about the wave nature of light. So we looked at the double slit experiment where we saw that a path length difference that the light travels between the two slits will cause an interference pattern on a screen. And in class we talked about the fact that that is a probability function of where you would see the light if you looked for it at some place. So we know that light propagates as a wave. And then we also looked at thin film interference. And so we saw that we could get constructive or destructive interference based on phase shifts and path length differences traveled in the thin film. So for those problems, we had to be really careful about if we were going from a low to high to low index of refraction, or from a low to higher index of refraction. And then you have to choose the appropriate equation to give you another phase shift of either half a wavelength or full wavelength, depending on what you are looking for. So that was light as a wave. And then this lesson is about light as a particle. So we'll begin to talk about the particle nature of light. As we discussed briefly in class, light has both wave-like and particle-like properties. Okay, so the first thing we need to talk about in this lesson is the energy of a photon. So photon energy is quantized. So photons can only have energy that is equal to positive integer multiples of the quantity hf. And this is a PRC equation. And so E is the energy of a photon. And we know the energy is in joules. H is Planck's constant. And that is on your PRC. And that is equal to 6.626 times 10 to the negative 34 joules times seconds. And then F is the frequency of the light. And we know that's in hertz. Okay, and then one thing you might have to be conscious of is just the units of energy. So here we give it to you in joules. And I would also say that you should remember the relationship 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. And so this is on the back of the PRC as well. And so is Planck's constant. Okay, so that's energy of a photon. And in the lesson objectives, we're asked to relate energy and power and intensity. So let's look at the equations that govern those relationships. Okay, so let's look at the equation for power. So in this equation, we see that back in PH255, we said that power is the rate at which work was done by a force, but more generally, power is the rate at which energy is transferred by a force from one type of energy to another. And so we see that power is energy per time. And we also know that intensity is power per unit area. So looking at this average power equation, we might need to talk about the power of a laser beam per se. And so for that, we would have to look at the power is hf over delta t. So that might tell us the power of some laser pulse given some frequency of light. And we also know that the speed of light is lambda f, so wavelength times frequency. So frequency equals speed of light divided by wavelength. And so we can sub this expression in here. And so we might say that power is hc over lambda over delta t. And so these are just some concepts that you might need to relate together. So the wavelength of the light, or the frequency, the time of a laser pulse, and then we can substitute this expression for power into here to talk about the intensity of some laser light. So I would just say be comfortable with the concepts of what intensity, power per area, power, which is energy per time, and then energy of a photon, h times f, or hc over lambda. So just be familiar with those concepts, be able to relate them together. Okay, so the next thing we need to talk about is the photoelectric effect. Okay, we've all heard about solar power, right? So this is just a quick little diagram of what a solar cell looks like. And solar cells, solar panels, work with the photoelectric effect. And so the photoelectric effect involves an incident photon with some energy actually ejects an electron from the surface of the metal. So those electrons that are ejected are actually called photoelectrons, and we know that current is the flow of positive charge carriers, or electrons in a circuit. So if we can get some incident light on a solar cell, we can eject some electrons and use those electrons to do something like charge a battery or operate your TI-30XIS, whatever that little blue calculator is that you guys have. So that's how those work. And so what we normally want to do is calculate the energy of the ejected electrons, or the speed of the ejected electrons. And to do that, we can look at a quick little diagram. Okay, so here's our metal. And we're going to say this metal has a work function. And the work function is the minimum amount of energy required to eject an electron. If you were to go to Wikipedia, which I'm reading from right now, it says in solid state physics, the work function is the minimum work or energy required needed to remove an electron from a solid to a point in the vacuum immediately outside the solid surface. So it's how much energy you need to get an electron off this metal. Okay, so we have a photon with some incident energy, and we eject an electron with some, let's say, maximum kinetic energy. And so if the work function is the energy required, the minimum energy required to get this electron to be ejected from this metal, then we can just write a simple conservation of energy equation. And that equation is HF, so that's the energy of the photon, equals K max, so that's the maximum kinetic energy of an ejected electron, plus phi, which is the work function. Okay, so those are the variables. Again, HF, incident photon energy, K max is the maximum kinetic energy of an ejected photoelectron, and then phi is the work function of the metal. And so all these are going to be in terms of either joules or EV. Usually work function is given in EV, electron volts, and so let's look at a couple of examples of a work function for some metals. So let's move that over there, and let's import this photo. Okay, so this is just an example again. Some work function of selected metals. We see that phi is given in electron volts, and this just is an example again. Okay, so photoelectric effect, again, this is the equation you need. HF equals K max plus phi, and then you might need to relate K max to 1/2 mv squared if you wanted to calculate, let's say, the maximum speed. So the reason we say K max is because this incident photon, if it collides with some electrons, or if it has some other things going on inside the metal, it might reduce this actual kinetic energy that you get. So this is assuming that we have no loss of energy in this process. Okay, so that's the equation you need for that. The last topic for this lesson is Compton scattering. Okay, so one photon-matter interaction that we just looked at is the photoelectric effect. This one's a little different. So Compton scattering involves some incident photon, incident on an electron, and what happens is we get a scattering of the photon off the electron, and based on the angle at which it scatters, we can see different frequencies of light or different wavelengths of light that come off. Okay, so let's say this is our incident photon, E equals HF. There's a stationary electron, and this might be our just before picture. And then just after this interaction, we can maybe draw the photon scattered at some angle, phi, and the electron might be scattered in some other direction with some velocity. And so that's what the Compton shift is. So photons, we know, have momentum because they have energy. So if photons, even if they're massless, have energy, we know energy is mass. So if it's moving, they have momentum, which we talked about with radiation pressure. So this photon will actually transfer energy and momentum to this electron. And so we have this conservation of momentum situation set up. And we can actually calculate the shift in photon wavelength that happens between the incident photon and the scattered photon. Okay, and so this is the equation we use to relate those two wavelengths. So we say the change in wavelength is Planck's constant divided by the mass of an electron times the speed of light times 1 minus the cosine of phi. Okay, or wavelength final minus wavelength initial equals h over mass of an electron c, 1 minus, cosine of phi. Okay, so in this equation, again, h is Planck's constant. This is mass of an electron. And this is on the PRC. Okay, and then phi is the photon scattering angle. Okay, so that's this angle that we said the photon scatters off in relation to its incident direction. So for Compton scattering, more generally, we can write this as change in wavelength equals h over mc 1 minus cosine phi. And in this more general equation, which is on your PRC, m is just the mass of the target. Usually an electron, but it's the mass of the target thing that you're scattering off of. Okay, so one thing to note about the Compton effect or Compton scattering is we get scattering at every angle, right? So we send a bunch of photons incident on some material with a bunch of electrons, and we can get scattering off at a bunch of different angles. When we apply this equation, we're just looking for the wavelength shift at one particular scattering angle. That's all. So I think it's just important to know that it doesn't just take place at one angle. It takes place at a range of angles, and we're just looking at the particular wavelength shift for a particular photon scattering angle. Okay, so that's the whole lesson. A couple things just to show you really quick. Okay, so this is one application of the photoelectric effect. This is how your NVGs work. So when you go to Buckner this summer or when you go to CTLT and you draw a pair of PVS7 Bravos or whatever kind of NVG that you have in your unit or they're out there at Buckner, this is how they work. So you can really demonstrate your nerdiness if you try to talk physics in the Army, right? So how does this work? Well, we have what's called a photocathode, and this photocathode, when it's bombarded with photons, ejects electrons, just like we saw with the photoelectric effect. So these ejected electrons hit this microchannel plate, which is an electron multiplier. So we get this avalanche of electrons that are incident now on this phosphor screen. And so this phosphor screen does kind of like the opposite. So it takes electrons and then it glows this green light that you recognize from your NVGs. And so this is called a phosphorescent kind of a process. Green is good because your eyes are very sensitive to it. So if we enhance dark image with green, you're more sensitive to it. And that's why your NVGs look green. It's this phosphor screen. It's that process. Okay, so that's NVGs. That's a lot different than how thermal sights work. Okay, so this is an image from a FLIR camera, FLIR. That stands for forward-looking infrared. So this does not work by enhancing an image. So this is taking visible light and multiplying that signal through this photoelectric effect and then this phosphorescent screen to just basically amplify the light, right? FLIR is actually taking an infrared light, so you have an infrared sensor. So this is what a FLIR image looks like. So I just want to highlight the fact that your NVGs are not thermal sights. They're light amplifiers or multipliers. FLIR, or your thermal sights, are actually taking an infrared signal or infrared radiation. And there are situations where you can camouflage yourself with visible light, but you can't camouflage yourself, or it might be a little harder to camouflage your thermal signature or your infrared signature. So aircraft will typically have FLIR or some other thermal sensors. It's just another good tool that you might see out there this summer. Okay, so that's it for this lesson. I think this video is probably longer than I wanted it to be, but that's okay. I will not be in class on Friday, and I know that a lot of you won't be due to Sandhurst and some trips and things. Some of you are going to, like I know the marathon team, Jason Black and Nikki Price, you're going to nationals, so good luck with that. I know a lot of other people are traveling and doing Sandhurst, so everyone doing Sandhurst, good luck. And then Monday for H hour, I figure if you guys watch this video, we can just review the equations and stuff. So that's it. Just remember that this is lesson 31. You have 40 lessons in the semester. If you subtract that one from lesson 40, you have 9 lessons left. Not too shabby. You take away 1 for the WPR drop next week, and you're really looking at 8 lessons left. So while it's bittersweet, and I really don't want to say goodbye to you guys, I do want to make sure we have some fun and learn some stuff the last 8 lessons. So do well on the exam, study hard, study the problem sets, study the suggested problems, and I know you guys will crush the test. So hope you enjoyed this video, and let me know if it was good, let me know if it sucked. Good luck this Friday and Monday, and I will see you all in class or in lab.